Hi everyone, if we could please quiet down. Today, Julianna is going to be presenting on seasonal rhythms in mice and unsaturated fats. Thank you.
Hi everyone, sorry for that. I wanted to thank everyone for coming today, and I'm going to be presenting on how some researchers found that unsaturated fat can alter clock phosphorylation to align rhythms to the season in mice. So first, I want to establish what the circadian clock is. The circadian clock is our body's internal, roughly 24-hour clock that regulates a number of different biological processes and behaviors. And these processes and behaviors are known as circadian rhythms. So some examples of circadian rhythms are our sleep-wake cycles. So our circadian clock tells our body when to feel tired and when to feel awake. It also controls the release of different hormones like melatonin and cortisol. It regulates our body temperature so that it's higher in the afternoon and evening and lower in the morning. And it also even manages our appetite a little because it tells our body when we're full and when we're hungry. And that makes sense because when you're sleeping, you really don't want to feel hungry. You want to feel full so that you can sleep peacefully through the night. But a key feature of the circadian clock is that it's not exactly 24 hours. For most of us, our circadian clocks are a little more than 24 hours. For some, it can be less, but for the majority of us, it's more. And what that means is, say I woke up today naturally at 9. If my body was only following my circadian clock, I'd wake up tomorrow a little later than 9, and that might not seem like a big difference. But if we look further into the future, like a couple of days, weeks, months, eventually I'll be waking up at 10 and then 11 and then 12 and so on. And what that means is my body is just kind of functioning later than it should, and my body's not aligned to the 24-hour days that we have. So as a response, what our bodies do is we listen to external cues and we respond to them to help make sure that our circadian rhythms are following a roughly 24-hour cycle. And an example of that is light. So if I go outside, my body knows that I should be awake if it's light outside, like if I see the sun or just light. And then similarly at night, if it's dark, my body knows that I should be feeling tired. So this makes sure that my circadian rhythms don't kind of stray too far off of our days. Now, how does this connect to seasonal affective disorder? Seasonal affective disorder is a type of depression that you can get when the seasons change, and it's most common when we're transitioning into the winter. And one of the known causes of seasonal affective disorder is a lack of sunlight. So what happens is our circadian rhythms are then disrupted or misaligned, and as a result, our bodies aren't kind of functioning properly, and someone with seasonal affective disorder might feel sad, they might feel irritable, they might feel increased fatigue or have an increased appetite, and they also might have trouble sleeping. And why is this relevant? Each year, an estimated 10 million Americans deal with seasonal affective disorder, but a greater percentage are expected to kind of experience milder episodes of seasonal affective disorder. And this relates to us at Pingree because since daylight savings just ended, the sun sets much earlier now. And for some of us, we might be leaving school when it's already dark outside. And that means that some of us probably aren't getting enough light, and that could cause feelings of sadness or just fatigue. So as I've said, our bodies use light as an external cue to align our rhythms to the day, like the 24-hour days. But within that, our bodies also need to react to how much light we're getting, because that makes sure that we're using light properly as an external cue, and our bodies function better when we're responding to if there's more light, less light. Because if there's light, if the days are longer, then we don't want to feel tired when it's like 7 p.m. and it's still bright outside. So what our bodies need to do is, in the summer, when we have longer days, our bodies need to delay or move our circadian rhythm, those processes, later. And then similarly in the winter, to make sure that our body's functioning at its best, we need to move those processes earlier or advance them. And this brings me to the idea of circadian entrainment, which is the process of syncing circadian rhythms to the day through external cues. And this brings me to what the researchers of this paper did. What they did is they looked at diet as an external cue, not just light. They wanted to see how impactful diet is and how it exactly influences circadian entrainment, or how we adjust to the different seasons. And what they focused on is this protein called period 2, because it's really important to the timing of our circadian clock. On a cellular level, what happens with our circadian clock is BMAL1 and clock are two transcription factors that enter the nucleus and bind to our DNA every morning at around dawn. And what will happen is they'll regulate the production of different proteins that we use during the day. But what's interesting about them is they also regulate the production of their own repressors, cryptochrome and period. And what happens is, during the day, levels of cryptochrome and period will build up in our cytoplasm. And then when we get to night and kind of towards the evening when it gets darker, what they'll do is they'll enter the nucleus as well. They'll bind to BMAL and clock, the transcription factors, and they'll rip it off of, or strip it off of our DNA to prevent our bodies from producing any more proteins that we use during the day. This way we can transition into the night, and that means that we're kind of following a 24-hour cycle, because it'll happen the next day. They'll repeat, and this is why it's important to the timing. But what makes period 2, one of the repressor proteins, special is the previous researchers have found that it can become phosphorylated on one of its serines, specifically serine 662. And they found that this phosphorylation happens through nutrient pathways. So this led the researchers to think, oh, how can we use period 2 to help explain how diet influences circadian entrainment, because it involves the nutrient pathways of what we eat. So the way that their experiment was structured is they fed mice a high-fat diet, because previous researchers have found that a high-fat diet impacts our circadian clock, and it increases the phosphorylation of period 2. So the 3 diets that they gave to the mice were high-fat diet, a calorie-restricted diet, and then also just a regular diet, like regular chow. And they gave them ad libitum, or unlimited access to these diets, to their food. And then at night, they monitored their activity, because mice are actually nocturnal. So they looked at their wheel running activity to see when they were moving and active. So before I get to the data, I kind of want to explain how to interpret this. So basically, the y-axis is the time and days of the experiment. So if we go down, that means we're going further into the experiment. And then the x-axis is basically showing their activity. So the black dots are actually like the footprints of the mice on their wheels. And then what we see here is we see like 0 to 24, which is like the time of the day. So if the line is moving to the left, then that means that they're moving their processes earlier. Things are happening, they're on the wheel earlier in the day. And then if they move it to the right, then that means that they're going later in the day, and that means that they're delaying it. So for figures 1b and 1c, what the researchers did is they simulated a transition into winter. So they went from equinox, which is 12 hours a day and 12 hours of night, to 20 hours of night and 4 hours of day. So what they tested is they looked at the high-fat diet and the regular first. And what we see here is you see that the black line is further to the left than the blue line, which is the high-fat diet, which means that the control, just regular like mice, are better than mice who had a high-fat diet at moving their processes earlier and advancing them. But we see the opposite effect when we compare the calorie-restricted diet because, as I said before, high-fat diet means increased phosphorylation, and calorie-restricted diet means like less phosphorylation than if you're just a regular diet. So what we see here is we see that the red line, the calorie-restricted diet mice, their line is further to the left than the black line, the control, which means that they advance at a faster rate. And you can see that here because the way that they show their rates is in hours per day by how many hours they advance on average per day. And you can see that here, the black line is the black dots are above the blue dots, and then here the red dots are above the blue dots. And then they also looked at the change into winter, the transition. So again, they started with 12 hours a day and 12 hours a night, and then they moved into 20 hours a day and 4 hours a night. And so the way that you look at it is the same. The dots mean the same thing. The X and Y axes are also the same. But what we want to see here is we want to see it move further to the right for you guys. And what we see with the high-fat diet is we see that it's kind of hard to see here, but the blue line actually moves a little further right than the black line. But to help like visualize that effect, they kind of put this into the figure as well. And what the ZT means is that's kind of the average time that the mice like delayed their processes to. So like if you think like 18, that means that they kind of started going on the wheel like at 6 instead of before at like, if it was at before like at 12 or something. And you see that the blue is above the black, so that means that the blue, they moved it later. And then if we compare it to the calorie-restricted mice, what we see is that the red line, because here we can just look at the lines, and the red line is way further to the left than the black line, which means that the ones who had calorie-restricted diet really were not good at moving their processes later and delaying them. So just to summarize those two figures to like remember, what happens is if you want to advance the rhythms and move them earlier in the winter, the mic's off, not bad. Hello? Hello? What? I have to hold it? Hello? Okay. So what we see here is that if we want to move to the winter and we want our processes to advance, the high-fat diet really sucks at it, and then the calorie-restricted diet is better. So that means that if we have more phosphorylation, we're better at doing it, and then if we have less, we're actually, if we have more phosphorylation, we kind of suck at it, and then if we have less, then we're better. And then we see the opposite thing happen when we're looking at the summer, and we see that if we want to delay it, if we want to move it back later, the high-fat diet is really good at this, and then the calorie-restricted diet kind of sucks at this. Now for the next two figures, what the researchers did is they wanted to make sure that it was the phosphorylation that caused the differences, and it wasn't anything else. Like they wanted to make sure that the phosphorylation is the main thing, and that's what changes things, and it wasn't anything else in the pathways or anything else that involves like what happens in your body when you eat a high-fat diet. So they basically mutated the period 2 protein in mice, and for the red, they mutated it to a glycine, which meant that it would never be able to phosphorylate. And then for the blue, they mutated it to an aspartic acid, which kind of mimics an always phosphorylated state. And what they found is they found that their results align with the results that they found earlier. So if we look at the winter season, the ones with less phosphorylation or like no phosphorylation at all functioned like this, the ones who were fed a calorie-restricted diet with a less phosphorylation. So what happened is they moved their processes much earlier, and they were better than the control. And then we also see that with the ones that mimic the always phosphorylated site, so it's a lot of phosphorylation, they did not like advance it like basically at all. And then if we look at the summer, we see the same effect that we saw earlier as well. We see that the mice that were never phosphorylated, that could never phosphorylate at all, they could not delay their processes and their circadian rhythms. But then the ones that mimic the always phosphorylated, and they were actually better than the control, and they were very good at delaying it, which shows that phosphorylation is what kind of causes the differences. And then to further prove that, what they did is they compared the effect of the diet on mice that couldn't phosphorylate to make sure that it was the fact that a high-fat diet increases phosphorylation and that's what makes them change. So what they looked at the mice that were mutated to never phosphorylate, and they fed them a high-fat diet and a regular diet to make sure that there was nothing else in the pathways, nothing else that was doing anything. And what we see here is that the difference in their rates is not significant, which means that they basically did, like, feeding them a high-fat diet versus feeding them a regular diet really led to no change in their ability to advance or delay. So that just further, like, establishes their results as true, and, like, it kind of proves that the phosphorylation is what we want to focus on. This is just to see a little clearer. If you can see, like, the lines are basically, like, next to each other. Now, what's next? Like, what are the future directions of this research? One, maybe because mice are nocturnal and they react to light and they're like, I want to go to sleep, and like we react to light and we should be awake. Maybe that makes some things different. And also the fact that we don't know if diet impacts our phosphorylation of period 2, because we also have period 2 as mammals. It's highly preserved in mammals, but we don't know if diet has the same impact. So maybe we could try this on like humans and just see that if a high-fat diet does increase phosphorylation. And then another thing is, if that's true, maybe diet can help with circadian misalignment, because if it can advance your processes, if it can delay your processes, that could be helpful for people who can't transition well in the summer. And then a final thing is, as like humans, like we don't get 24 hours of daylight, like 20 hours of daylight. We kind of have artificial light sources like these. So maybe what researchers could do is they could simulate having like artificial light at night and see what happens with mice then, and see what the impact of us kind of like being on our phones or just being in a like brightly lit room at night has on our circadian clock. So now I want to thank my journal club staff who helped me on this, which is Anna and Julia, and then I wanted to thank Mr. Maxwell for helping me, and then also all the teachers who give extra credit, and just everyone who came in general. Does anyone have any questions? We can take one question. Okay, Eric.
Can you go back to the figures, like the one?
One B.
Yes. No, one more. Yeah, so is there any difference between regular chow and control chow?
Regular chow and control chow are like the same. I don't know why they changed